Alberti, mamen çfarë paper kemi caktuar në kaluar?
Jo, profesor, nuk e marr mend se nuk I kam këto.
Oh, po si në fakt, okay, duket se s'na ka bëtin herën që kaluar.
Jo, nuk isha.
Okay. Për të shikoj unë se mbaj me nda kemi. Atëherë shiko pak glastre plenoptik. Alberti, mirë. Është 2013 glastra.
Okay, profesor, në rregull.
Shikoj pak këtu, do të jetë aty te edhe kjo është plenoptik.
Me litografia e profesor pak me dritën me lazer.
Për Stefanos, për ti po flet?
Po unë, kjo që e ky djali, atë po shikoja pak unë.
Ta glasrin e ke pati Stefanos. Okay. Atëherë
po hidhen një sysh dhe shpejt, më troj që se pash kishte më bet lazerash.
Okay, në rregull. Atëherë çfarë themi ne këtu, nëse shohim të papert, po Alberti më që paska lexuar Stefanos, nuk është se ashtu, po tjetër shikoni paper tjetër? Sa të shikoj pak këtu unë, optical single pixel imaging cell function. Presim dhe Haridin, apo kë kishim tjetër? Atëherë.
Profesor, do I pyetja unë si është e lënda për shkak në term e final.
Kjo do keni projekt shumë.
Është projekt domethënë research e gjitha, a?
Po.
Ndahemi në grupe?
Këtë nuk e di. Do të shikojmë se do heci puna. Normalisht grupet ndoshta mund të kenë të mijat e veta, katëqiet e veta, po do ju them unë. Por që tani do ju përcaktoj gjëra që duhet të bëni. Atëherë unë mund t'ju them kështu juve. Një sekond, page. Për shembull, atëherë ose Alberti lexoj, po ashtu vazhdo lexo atë Albertin, nëse ke mundësi atë çfarë quhet plenoptic something. You go with it. Alberti, atëherë Alberti ka këtë. Franki mamen çfarë thashën e kaluar, çfarë paper i caktuar?
Me thënë drejtën profesor nuk e mbaj mend.
Okay. Atëherë Harildi që kemi këtu, Harildi kishte PPM dhe një corrigendum. Këta në shikoj diçka unë si në Optica. Okay. Single pixel imaging. Franki, po shiko, majni me këto, edhe unë do të sugjeroj këtë. Hapini kompjuterat që keni në shtëpi, hapini edhe Wordin, edhe filloni shkruani review-n. Dhe kur them review-n, bëjni review-n siç e kemi nisur këtu bashkë, herën që javën e parë në fakt. Dhe këtë do dorëzoni nesër. Dakor? Kjo do jetë si first task. Pra, ekranin tim besoj e shikoni tani?
Mirë, që do dorëzojmë nesër, profesor?
Nesër do dorëzoni një Word si kjo që kam shkruar këtu.
Në lidhje me një nga këto
pepra që kanë caktuar, do filloni shkruani. Për shembull, çfarë nisim ne? E zëm. Në rastin e po të kapim këtu për shembull, në rastin e Albertit. Alberti për shembull ka ndërkohë prit saktoj gjithë nga paper-un, pra Franki thash diçka unë ty? Jo, okay.
Profesor, më the këtë single pixel imaging të 2018-s.
Okay, single pixel imaging. Okay, dakor, shikoj atë. Alberti e ka të qartë. Atë edhe ti Stefanos ti pa shumë mbaj po të njëjtin paper nëse ke lexuar, se po deshë të jap të caktojmë një tjetër. Franki caktuam, Alberti po, Alerti mamen. Çfarë po të them se harroj shumë? Alerti mamen çfarë dashën e kaluar? Alerti lexonte 2019 filizin? Edhe diçka tjetër, këto paperet kur të flasin për referencat e paperave, do i lutem, jo me fjalë, nuk është me detyrim, por që të kemi një gjuhë përbashkët, do i sugjeroj të përdorim këtë terminologji. Vitin e paperit kur është publikuar dhe mbiemri i first author. Për shembull, paperi që do ketë alertë është 2019 filiz, edhe në keyword që mund të jetë për ta dalluar. Për shembull, kjo është paperi i alertit. Noti kamera, është Albertit. Vetëm çfarë viti është kjo noti Alberti?
2013 profesor.
Si ka emrin e autorit i parë kështu? Glastre.
Glastre.
Glastre për noti kamera. Edhe okay, so we move ahead. So this was it. Then
Profesor, fal.
Po.
A mund ta bëjmë dhe një përmbledhje të shkurtër se si ta bëjmë këtë review-n?
Do flasim për këtë. Për shembull, do them diçka shkurtër, Franki, ma thuaj çik paperin që kishe ti?
Të 2018-s single pixel imaging.
Kush është autori i parë?
Ja, një sekond. Kazuki Ota.
Okay. Vetëm last name is enough. Mbiemri Ota është?
Po.
Okay. Stefanos, ti kishe paperin Albertit 2013?
Po, atë më se javën e kaluar ti mua që e pash pa.
Okej, shumë mirë. Shumë mirë. Hidheni sy tani shpejt. Harili. Po.
Ta mund të shtysh me ditë pak nëse nesër për lejon, mundem kem kohë ta mbaroj deri.
Jo, nesër deri në darkë, dakor? Nesër deri në darkë. Dhe vim këtu. Harili, çfarë paperi caktuar herën e kaluar ne? Ishte FPM, Fourier Ptychography, po s'majme në vitin.
Profesor, fal, nuk kam qenë radhën e kaluar e se di çfarë teme kam.
Po, Harili, zëri jotë është ky?
Jo, Andi.
Andi, përdisjon se. Okej, Andi, dakor. Andi, po më sigaret më Andi. Dakor, Andi ti e këtu, atëherë Andi ti hedhim sy këtu te materialet këtu. FPM, Corrigentum, Sinha, Optica. Andi, është një paper shumë e bukur, shiko këtë Sinha, që ka Sinha 2017. Sinha. Computational imaging, Lensless. Deep learning. Tani, në fakt do bëjmë dhe këtë ne. Sot, kur të marrim mësimi, që do thotë s'do vonohemi shumë, s'do keni shumë kohë, atë versionin ç'a keni bërë sonte, do ma dërgoni që sot. Pra filloni të shkruani një dokument siç po e shkruajun, atë do filloni të shkruani dhe me një shembull që do bëjmë, do zgjidhim ato pepra dhe do flas për atë. Do mundoheni të bëni diçka të ngjashme. Atëherë Alerti, Alberti, Franki, Stefanos, Harili, Andi, kë kemi lënë pa përmendur këtu, Alertin e kishim. Alerti, Alberti, Andi, Frank, Harili, Stefanos. I kemi të gjithë atëherë. Okej. Dakor. Pra jemi deri tani që kemi 6 vjet në klasë, në klasën tonë. Faktën prezant për sot. Okay. So so these are some papers that you can go over. So this is week 2. Paper 15. Now, whenever you do something, let's say you are going to start your master studies, okay? And I would strongly suggest that all of you keep a Word document or a folder where you put everything which is important. The first part is a Word document, which will be your master doc, okay? Master doc, and this master doc, I strongly suggest you to insert quick award at the table of contents. No, this is not the table I'm talking about. Where is the table of contents? Table styles, insert. I always forget this one. Çuna kush e mamen ku gjehet kush ka table of content?
Tek referenca do.
References? No, it's a document elements. Okay. Okay, so here we are. So I suggest you to start working and in this master doc where you are going to enter all the information that you have. Now you need this one because let's say once you read the paper, you find it interesting, and then you say you're going to use it, but then after 2 weeks you lose it. Okay, you forget the paper, you forget the year, the author, and when you write down your master thesis, you won't remember anything. Okay, so you start preparing a Word document like this. Now this is the title. You made the title here like heading 1. If you make this heading 1, you'll be able to see this like this. So title, research methods, introduction, literature review. We had here the abstract. So even the abstract, we can make this one. Is this heading 1? It is. Why can't we see it here? Okay, introduction, it's here. Maybe the abstract we cannot see because it is in this format. Now probably we will see it. So let's update field, entire table. Okay. I don't know why I don't see the abstract separately. Anyway, it doesn't matter. So this is introduction. So whenever your format, when you write your thesis or anything, so what you can do is also this one. When you write the thesis, I strongly suggest that you could also use these insert page breaks. Okay, page breaks. So you have this on the other page. This would be a good way. Then we also mentioned the importance of trying to keep together all your references. And for all your references, we suggested you to install Mendeley. Now, I guess even when you insert, so there is this Mendeley desktop toolbox, which I guess you started to install it from the last time. So you can open it, and then it will be much easier for you when you enter the references. Now, when it comes, so let's see here. So okay, so here we have all these references which were easily insertable. Now, let's see how we can conduct. So here I have this. Okay, so Mendeley is up. Now let's see. Where is this? No. So let's have a look at this paper. At the paper of I think this was Andy. In the paper of Sinha. So here we have a paper. So the first thing that you have to look for is the quality of the journal. Okay, so let's see here. We mentioned that in the first week, first to check. So you look at this journal, author quality. Okay, success rate, recognition of the author. So here, when it comes here, we have this paper, Lensless computational imaging through deep learning. First of all, how many authors there are? There are 4. Okay, 4 authors. This is something you don't write in the review, but you figure out this is like a good university. It's MIT, it's Massachusetts Institute of Technology. It looks like a strong group, and there is also a group from Singapore MIT Alliance for Research and Technology. So apparently it's also MIT affiliated entity. What is interesting is also this line here, received 27 June 2017, revised. They revised it here, so it takes the revision June, July, August. So it has taken like 1 month and a half. So in 1 month and a half, they have accepted this paper, which means that this is a really good paper. They have moved forward very fast, and 1 month later they have published it. Okay, it's good also to figure out or to keep an eye on the timeline that is taken from the submission or from the reception from the journal by the authors up to acceptance and to the publishing date. So we look at this paper, and what is the next thing that we look? We look at journal quality or conference quality. We also noticed in the first week, we said that when we read the paper, it should take us 5 minutes to read an abstract. Okay, so here there is an abstract. This is a very concise abstract which says deep learning has been proven to yield reliably recognizable solutions to numerous classification and decision tasks. Okay, so apparently they discussed the deep learning for classification and decision making. Actually, this could have been written like decision making tasks. Here, look at this abstract. They are so confident of themselves that they put an abstract of 3 to 4 sentences. Okay, so they say here we demonstrate for the first time to our knowledge that deep neural networks can be trained to solve end-to-end inverse problems in computational imaging. We experimentally built and tested a lensless imaging system where a DNN was trained to recover phase objects given their propagated intensity diffraction patterns. Okay, so let's see. So we have, wait a second. So let's assume when you read a paper and you write about this paper, this content is traditionally expected to be in the literature review. So assume that Andy is going to write this one. We are going to do the following. We have, so you can say that Sinha and co-authors. Here you can put here 2017 have worked on let's say have worked on deep learning for computational imaging. Now, what I understand from the abstract, okay, so we try to understand so the first sentence is the general sentence. We have said that whenever you write the abstract, so we can say here actually their abstract has the generic sentence. What is a generic sentence? It's a sentence which it can be so general, like the moon is very romantic. Okay, you can write this one, everybody can accept it as the first sentence of a paper. Here they also say that deep learning has been proven to yield reliably recognizable solutions to numerous classification decision tasks. Okay, now what is deep learning? Deep learning is a way to provide to a system. So you can even, or let's do it like this. We can write this one in detail, assuming that the reader of your thesis is going to be a student. Okay, so a thesis can have simple definitions, assuming that you could structure your thesis. So your thesis is repetition. You can forget this. A thesis, assume that you can structure it. You can structure it like a tutorial. So you can have a thesis which will look like a tutorial. People learn something from that. And once it has such a structure, you can have simple definitions. What is also very important is this. You are constructing, now that you have started to write on this Word document, you are constructing your master document. And at this stage, since you are writing for yourself, you can include even stupid things. Okay, you can say, for example, definition. What is diffraction? Okay, because this paper is talking about diffraction. Okay, so you can write a definition here, and then it's not. You should not be ashamed, because when you give the final touch of your thesis, you can always take away this stupid or simple definitions, not stupid, but very simple definitions, and then you can remove these, and you have your thesis. Or you can have up to the final day when you are going to submit your thesis, you can keep these. Then you do a save as. You cut out all the little details, and you have a better quality of a thesis. So you can have even these definitions. What is diffraction? Okay, define it. And then what we see here from the paper of Sinha, the paper of Andy, it looks like their abstract has a generic sentence. A thesis can have simple definitions. Assuming that you could structure it like a tutorial, this would be very important for new students when they want to learn about something new. Sorry, okay, no, this was a mistake. Okay, so then they had this generic sentence. Here we demonstrate for the first time to our knowledge that DNN, deep neural networks, can be trained. Okay, so here we have the keyword computational imaging. What is computational imaging? So here we have another keyword, which is, now actually we say this is a keyword, but let's see whether this is really a keyword. So let's look at this part. Whenever you write a paper or a thesis, you should have a list of keywords. Let's see what they have identified. They have identified inverse problems. Okay, what do we understand from these inverse problems? Let's keep this one here. Inverse problems, we keep this here. Pattern recognition, I think most of us might have a feeling of what this is. This is not very technical, but we can pick it up. Phase retrieval. This is also a very important term. And you have computational imaging, which just by looking at the abstract, I was assuming that this computational imaging, this could constitute one of the keywords of the, so this is the Mendeley desktop. So apparently this is one of the keywords. What is computational imaging? So computational imaging, especially for you that are students in electronics engineering, this includes the use of algorithms to enhance, to do what? Let's say to enhance an image. Okay, enhance. Now actually increase the contrast, increase the resolution. So you can do, imagine now you have a microscope or you have a camera that you want to image something, or you want to image using a specific wavelength. You want to image planet Earth. Okay, you go at a very high distance. You don't use optical imaging. You don't use the wavelengths that are from 400 nanometers to 700 nanometers. And I'm sure you know this very well because you have taken a course during your bachelor studies regarding this. But you are going to use IR imaging. Okay, you use another, or you might even use UV, ultraviolet imaging, which is invisible to the eye, but at specific distances and specific length scales, you can image at a very good, satisfactory resolution. So, but this resolution, it is a function of the wavelength. So what does this mean? So increase the resolution. Resolution is depends, or is a function, depends on lambda. I'm going to write this one, or wavelength. Okay, but now, so this is limited. So it looks like if you select the wavelength, you have the limited wavelength, right? So which means that what is the wavelength of, let's say, red light? Who can answer this one? Saka drita kuqe, saka gjasin e valës. Okay, anyone? So this is from 400 nanometers to 700 nanometer. Okay, no one can answer this? Alerti? Alerti, sa është drita kuqe? Sa ka gjatësinë e valës?
Nga 400 deri në 700 apo sa?
Po, kjo është nga bluja te e kuqe. E kuqe është diku afër 700-s. Okay, Harry, that's true. So 650 deri 720. So that's correct. I cannot shift to this word. Okay, so let's say you are in the red range. So red color, it's something like 632 nanometers. This is equal to 6 times 10 to the power 2 times 10 to the power minus 9. Now, instead of this 6, you are engineers, you can write instead of this 6, this is 10 to the power 1. So what we get here, this is equal to 10 to the power 1 times 10 to the power 2, 10 to the power 3 times 10 to the power minus 9. This is 10 to the power minus 6, okay? What is 10 to the power minus 6 meters? So we are still talking the wavelength of the red laser. This is equal to 1 micrometer, or you can say 1 micron. So, okay, that's good. So if this is the resolution, now imagine for a moment, what if you have blue light? Blue light, it has a wavelength around 400 nanometers. Now 400 with respect to 700, it's like 100% difference. So it's like half, okay? Or from 400 with respect to 400, the upper range of the visible range of the optical range is like 100% higher. So this means that going from red to blue, you go from a resolution from 1 micron to 0.5 micron, okay? Now this is the resolution of the system, and this is like fixed, okay? You cannot beat this up. But with computational imaging, employing some algorithms, what one can do is that this 1 micron resolution with the correct algorithms, but you need to take a lot of measurements, because it is impossible to get one measurement and then go and beat up the physical limitations of a microscope, okay? But you need a lot of measurements, a lot of images, and then you implement computational imaging, and then from 1 micron resolution, you might be happy, or you can do it, because this is possible. You can go down from 0.2 to 0.1 micron. So you improve your resolution. If you are using blue light, maybe you can do something better. You can go, let's say, 0.05 to 0.1 micron resolution. Okay, so this is what computational imaging is about. So you can use it to enhance an image, increase the contrast, increase the resolution, or you can use this one for image fusion, image reconstruction. Actually, reconstruction is a very important keyword. So let me write this one, image reconstruction. Good. So this is what computational imaging is about. You can write the definitions like this in your thesis, and you can say computational imaging is a very important area. So I can write this. I can continue like this. Is a very essential or important. You can find other synonyms. Okay, you can always use the word processors to pick up smart synonyms. So essential, indispensable. This looks like a very crucial. Crucial is a good word. So it's very crucial area of research. It's a very crucial area of research. What should I say now? It's a very crucial okay, there is a very crucial area of research. Okay, that's good, comma. And recently, many research groups are intensively publishing in this area. This indicates that this is an indication. This indicates that the area is a good one. So let me say it this way, okay, is a good one. So if people are publishing in the last 2-3 years, then it's a good area. It's a good area of research. Computational imaging is a very hot topic. So if you read any paper on this, be sure that you're going to learn a lot of things. So these were the keywords. We're still working on the paper of Andy. So okay, we learned these keywords, and let's see. But now let's try to understand what they have used. They have experimentally built and tested. This is very good, actually. So when you read this paper, it looks like, why can't I use this one? I want to automatically shift here. So it looks like this is the paper. CEN and co-authors, they have done this one. These are their keywords. Their paper is a let's say research paper, pure research. It is not a review paper, because you could have review papers where no new results are presented, but they do a review of different areas. Now, different areas. Actually, for a specific topic, they cover the major publications in a certain area. Apparently, this is a research paper because they present for the first time experimental results of how a lensless So they have built and tested a lensless imaging system where a DNN was trained to recover phase objects given they propagated intensity diffraction patterns. Okay, so now you know that you are electronics engineering students, so you should understand everything that is written in this abstract, okay? I mean, if you don't understand it, you go back to the textbooks and you are sure you can find it. If you cannot pick up the information right away, since you are engineering students, you should never memorize one thing, but you should be able, from your background or from your bachelor studies, to understand something in 5 minutes, okay? So many things, especially to very good bachelor students, should take or could take 5 to 10 minutes to understand it. If you can understand something in 5 to 10 minutes, then you should memorize nothing, okay? If somebody asks to you, do you know this? You should simply say, I don't care. You say this one within yourself, okay? Don't say this out loud, because I can read it, I can understand it, I can do it, I can implement it, okay? This is how you may approach to a problem. So now let's see. They have recovered phase objects. So apparently, just by looking at the intensity diffraction patterns, so what they have done, let's understand what they have done in this paper. So the authors have measured diffraction patterns. They have acquired diffraction patterns, and from these patterns, they have not identified, this is not the best keyword, but you can say that it's something they have deduced, is a good word, deduced, because deduction is something that you see an event and you can deduce that something bad happened. You look outside, you see that it's the cars are wet, then you say, okay, apparently it has rained before, okay? Or so there was rain, they have identified, deduced the value of the phase of the imaging. Now this imaging, this was lensless imaging. Now lensless imaging. Now the thing is that, okay, so they have done this beautiful work. Now what is diffraction? Diffraction is a pattern that looks something like this. Let's see what is diffraction GIF. Let's try to identify what is diffraction GIF. So these are images, and I wanted to see a GIF, if you can pick it up. Sometimes you can find beautiful GIFs online, so this is the diffraction, okay? So this diffraction, this is how it looks like. Okay, all of this. Now, diffraction, it is really good. The simplest way to talk about diffraction is the bending of light, okay? So if you put a piece of glass in front of a laser beam, it diffracts, okay? So if it's not perpendicular, if it is perpendicular, you have no change of the direction of light, okay? Then you don't have diffraction. But you just change the direction of the piece of glass, or a semiconductor, or a plexiglass, very jump plexiglass, or a conductor or a semiconductor, where light can propagate even to some allowed depth. Then we call this diffraction. So the bending of light, the change of direction of the light, the change of direction, this is called diffraction of light. Then what we see here is that we have a plane wave. Can you see my mouse here? So you have a plane wave which is passing through a small aperture, and then we see that the light is changing direction, okay? Even if we had only one edge. Edhe po mos ta kishim këtë pengesën këtu poshtë, prap ai diffraction do të ndodhte sepse we have bending of light. But diffraction measures amplitude. Now we want to measure, we don't have the phase information, but apparently they have figured out a way to look at the amplitude information and pick up the phase. Now this is how much I can pick up from the abstract. We have to read this a little more in detail. Probably it might be exactly what we predicted or what we just talked about, or it could be some twist which we are going to see. So we're at the abstract. Then what do we do next? So actually we went a little fast, but it was only not fast. We went a little slow. We spent too much time into going over the abstract. But then what is the next thing? So we are reading this, okay, Chen, we are talking about Sinha and co-authors. This is abstract, what we gather, what we learn from abstract. What is the next thing that we need to read? Who can answer this? What do we read after the abstract in a paper?
Introduction.
No, conclusion. So you read the abstract, then you read the conclusion, okay? So I've said before, the abstract, it should take to us 3 to 5 minutes, especially this one, which is short, we should read this. But thank you for your minutes, whatever this is, minutes. So thank you for your input that you suggested to be an introduction, but including also last time, we said that we should read the conclusion because we want to acquire in as short time as possible whatever the paper is about. So let's see here. We see some graphs, okay? So conclusion and discussion. This is very concise paper, okay? So they're wasted no paint, no pen, no pencil. So they say that the architecture presented here. So apparently the architecture, this is the architecture of the deep neural network. So the way that they put the layers, okay, this is something that probably we don't have much information so far, but we can go over it. So it looks like conclusion, the architecture presented here was deliberately well controlled, comma, press here, with an SLM creating the face object inputs to the neural network for both training and testing. Okay. So the architecture with an SLM creating the face object inputs to the neural network for both training and testing. So apparently they are using an SLM. We're going to see what this SLM is about, okay? But it looks like they are generating their own face object inputs, and they are going to use it for training and testing. Whenever you have, apparently from conclusion, we have training, because deep learning, it's about training the machine, the computer, or the computing unit. Actually, I like this keyword, computing unit. Why do we call this computing unit? Because we could have FPGA, when you can do computations on this one in a very fast way. You can have Raspberry Pis, which are computing units, and you can assume a few more. So they train the computing by using training dataset and testing dataset. Okay, let's go here. And then this allowed us, them, the authors, to quantitatively, this is a very important keyword actually. Often, few publications or few theses, you can find that they can provide qualitative reports, okay? So they judge on the quality of the outcome just by using probably human perception. They give a qualitative, they say it looks better. But to provide quantitative analysis, this is very important. They claim that they have quantitative analysis. So this allowed us to quantitatively and precisely analyze the behavior of the learning process. Good. Application-specific training, for example, replacing the SLM with physical face objects for more practical applications, we judged beyond the scope of the present work. I did not understand this sentence at all. Let me read this again. So apparently, training and testing allowed us to quantitatively and precisely analyze the behavior of the learning process. Okay, application-specific training. Okay, so they have such as replacing the SLM training. This sentence I don't understand again. Application-specific training, we judged beyond the scope of. Okay, example. Application-specific training, example, replacing the SLM with physical face objects, formerly we judged beyond the scope. Which was judged. I think this is a misspelling. This should not be we judged. It doesn't mean anything. Maybe this should be like was judged beyond the scope of the present work. Okay. I thought, okay, application-specific training. Since this sentence makes no sense, apparently they ato kanë thënë, okay, kjo lloj analize e kanë konsideruar sikur nuk i përket, është një fazë më e lartë se sa punimi këtu. Okay. But this sentence, in this way that we read it, it has no meaning. Other obvious and useful extensions would be to include optics, example, a microscope objective for microscopic imaging in the same mode, and to attempt to reconstruct complex objects, imparting both attenuation and phase delay to the incident light. Okay, this is something interesting. What we observe here, this is very important sentence for some readers, because they say that apparently whatever they have done, they have not done microscopic imaging. So from the conclusion, we see that they propose that the use of microscopes could be the next step in research. Probably these research groups, they are from MIT, and we should look for their publications. Most probably, if they say it like this, from 2017, probably they already have done it. But anyway, it's a good research direction which you can immediately identify. This is a paper of 2017. Okay, it's not something like 20 years old. So this can really serve as an indication of what could be useful to study afterwards. From this sentence we learn that, but what is interesting is that unë s'kam lexuar akoma çka kanë arrit këto. Sepse këtu për shembull thonë që this was beyond the scope of this paper. If I read this sentence correctly, then they say what the extension could be used here. So they use you can use microscopy. And they say imparting both attenuation and phase delay. Now, I know that all of you in this class, you know what I'm going to talk about. Attenuation. So they talk about attenuation, and they call about phase delay. In electromagnetic waves, which one is the parameter which represent that attenuation? Who can answer this? Alberti. Alberti në pyeta, po fillojmë sipas alfabetit. Alberti, kush është attenuation constant në electromagnetic wave?
It was that alpha.
That's correct. Okay, is this alpha? Okay, so we know this alpha. We can make this a little more beautiful. Let's see. We make this symbol. Alpha is the attenuation constant. What is the unit of attenuation constant? What is the unit? Albert, can you pick it up?
I don't remember any unit.
But you should, actually, Albert, you should, because look at this one. We know that electric field, it's always equal to E0 times e to the power minus alpha z times e to the power minus beta z, but here we have a j, okay, times e to the power j omega t. So this is, let me put a comma here. So probably you do remember this expression. So this was the wave propagation, okay? And now I'm sure that you know all of these, all of these, we have seen it. So you know that this is the amplitude, and we see that apparently if there is an attenuation that they talk in this paper, the amplitude is going to change like this. So this is E0 initial amplitude. This is Greek alpha. Okay. Oh, I made it. No, this was a mistake. I just want to make this a symbol. What happened to this? This is too much miniaturized. Okay, let's leave it like that. Alpha. So the attenuation is here, but you are right, Albert. This is the attenuation constant is this alpha, but the phase constant is the beta. Okay, phase constant. This is unit of radian per meter. Because wait a second. Yes, it is phase constant, phase, but this is meter inverse. The unit of alpha is meter inverse. Why? Because this is e to the power minus alpha z. Okay, and the minus, since z is measured in meters, alpha should be inverse meters. And also omega. What is the unit of omega here? Unit of omega should be radian per second, because time t is second. Okay, so this is how we can pick up. And the propagation constant, there is a gamma. I don't know how is the Greek gamma here. This is alpha plus j beta. So this gamma, most probably you do remember this. No, apparently it's Greek little gamma. No, okay, this is it. So I'm sure that you have seen this in your bachelor studies. The symbol. This is beta. I think we covered it. Symbol. Okay, so this is the propagation constant. This is the attenuation constant. This is the phase constant, and we see that these authors, they are talking about that somebody can use a microscope and then they can pick up both attenuation information, how much the wave is attenuated, and this attenuation constant, this is a function of the properties of the material. Okay, so which means that this depends on permittivity and permeability. But biological systems, when they use in a microscope, actually they don't always have magnetic properties. So maybe the relative, but this now, my last minute, this could be a little extra information, but I'm sure at least this, you already know this. And when you read this paper, we should be able to understand the significant anticipated benefit in the later case is that it would be unnecessary to characterize the optics for the formulation of the forward operator. The neural network should learn this automatically as well. We intend to undertake such studies in future work. Of course, we have already done it, because this is 2020. So if we search for the papers of these authors, probably they have already done this beautiful work that they suggest in 2 sentences. Okay, so we're at the abstract, we're at the conclusion. The conclusion of this paper is so short, we don't really understand too much. But in principle, it looks, it's going to be something like this. What they are doing, apparently, they are providing, this is a good diffraction pattern, okay? This is a diffraction pattern, and apparently this is electron diffraction. So you see how this is changing. So what they are doing, they are giving different images of this diffraction, which is composed of bright spots. What can you learn from these bright spots? What is important in these bright spots is the distance between those, okay? And there is a different distance between some spots. Wait a second, how can I make this full screen? So there is a bright spot, and electric diffraction is not something you don't know, it's just the Fourier transform of a well-structured feature. So let's look at this one. Oh, this is beautiful. So they show this bar here, which denotes the distance between two little dots. But we can also define a distance from one arc to the arc to the other. This is another distance. And now what they are doing in this paper, apparently, they are providing the distance between these bright spots, and they are trying to predict what is the phase information, okay? But they do deep learning. What does this mean? They have a data set which they provide to the network, both the phase and the diffraction pattern. So they give the phase and the amplitude. And they give 100 images or 100 data sets with both the phase and the image. But they belong to different images. Then what they do is that they bring a new data set where they give only the amplitude, and they try to predict the phase. Now, since they have used a training model, most probably the computer is going to do a good job. For sure, not a bad one, a good job, a satisfactory one. But in principle, apparently, this is what they have done. So Andy, that is going to write the report on this paper, this is what he might discuss. Now, we read the abstract, then we read the conclusion. What do we read next? Next, actually, there are some aspects, but we say it here. Where is this? Abstract. We read this first. We read conclusion. We figure out what this is about, and then we check. Actually, then we can start with the introduction to understand what the paper is about, and for an experimentalist. So we could say here, now, this is not a rule, okay? You can say, it's not that, oh, I cannot read the introduction because I have not read the conclusion yet. But we read these two first so that we can pick up the major information on the paper as fast as possible. Then we go to the introduction, we try to understand what is going on, and then experimental section is very essential, okay? Because experimental or results section, sometimes I might call it results section. In the results section, what is the most important thing that you should be looking for? In this section, this is the most important element. If a paper has figures, a figure is worth 1,000 words, okay? Then you look at, let's say, let's go to the introduction. Let's have a look. And, okay, so they say neural network training can be thought as a generic, they even use a generic keyword. Of course, you start the introduction, the abstract with very generic sentences. So you don't jump immediately. They've used deep neural networks since the 50s. They give, in this paper, we propose, so let's see what they say. So they say, in turn, they have been applied in diverse domains, playing complex games on Atari, playing Go, object generation, object detection, image processing, colorization, deep learning, in painting. In this paper, we propose that DNN may learn to approximate solutions to inverse problems in computational imaging. So inverse problems, this is called inverse problem because you can obtain the inverse, you obtain the final result, which is the amplitude on your camera, and then you try to predict how the phase has generated. This is one way how we can define an inverse problem. Then it says a general computational imaging system consists of physical part and computational part. Yes, okay. This is a very good definition actually, because when we were talking about computational imaging, if we have a look back here, we said that computational imaging, we can have a physical limitation. So physical limitation of a system, it could be 1 micron or 0.5 micron, right? But we can always beat the system. We can always cover for the deficiencies of the physical system by using algorithm. So we said here, so we can decrease the resolution from whatever it is here, from 1 to 0.2 to 0.5. And this is a very beautiful sentence, which says that consists of physical part, which is the lens, lentja. Lentja, po që e keqe, lentja e fotografisë ose e mikroskopisë, atë s'ke çfarë i bën. Po kur është lentja e keqe, ti mundohesh ta përmirësosh jo lentën, mundohesh përmirësosh imazhin duke përdor algoritma për cilat lentja do ta jetë kurrë atë qartësi. In the physical part, this is beautiful. So we learn also here. In the physical part, light propagates through one or more objects of interest. Yes. What is the object of interest? Is the object that you want to see. Okay. As well as optical elements such as lenses and prism. That's true. Finally, producing a raw intensity image on a digital camera. Okay. Now, the raw intensity image is then computationally processed to yield object attributes. That is, example, spatial map of light attenuation and phase delay through the object, what we traditionally call image and quantitative phase image, respectively. So when you took electromagnetic waves, the lecturer tried very carefully to make it clear for you that beta, it represents the quantitative phase imaging. And I remember that some of you did the project on phase contrast imaging. And this phase contrast imaging, 2 or 3 students from your class reported that that beta, which is in the propagation constant, which is this element here, this information is used to pick up phase contrast imaging acquisition. But the alpha is bright field. So, for example, this alpha, which is the attenuation constant, this is responsible for the bright field microscopy. So, microscopy or bright field imaging. But the phase constant, the beta, which is going to be a Greek beta, this would be phase contrast microscopy. I have to put here phase. Okay, so we go back here. So we are learning it. This is introduction, but this is really a very good way to start the paper. So they say that the computational part of the system is then said to have produced a solution to the inverse problem. So they try to obtain. Wait a second. So the raw intensity image. So the raw intensity image would be this. In fact, you look at this. You look at these bright spots, and then you try to predict what is the phase. Because from the raw image, we computationally process these images, and we yield attributes, including the phase delay. Okay, this is a difficult way to do it, but it is doable. Especially, and let me say also one thing: this paper, or doing training and testing by providing images for let me think. Images of intensity images, providing a lot of images that look like this here in this slide. And the phase, doing training is a very easy task. It's not difficult, okay? Of course, to write a paper, you need also to understand this equation here, which you already know this, because, for example, we see here that you have a quantitative phase retrieval. You see this phi, Greek phi. This is, here you can see the exponential, which is a propagator actually, represent the optical field purely phase modulated by the unknown object phi. Okay, so apparently there is an object which is going to modulate the phase information. And let's see here, the measurement after propagation by distance is a raw intensity image. Yes. And the raw intensity image, it depends on the attenuation by the alpha, actually. Anyway, so these are some details. Okay, we can read this again. This is a 9-page paper. 1 page is references, but this is a lot of information so that we can acquire from here. But then let's go to the results. Oh, here there is an experiment. This is beautiful. Apparently, and then what is very essential, actually, for all of you, I would strongly suggest in the experimental part, this is very important to do the following. So read the experimental section. In fact, these are two different things. Experimental section, let's put this one heading 1. What we really care the most in here is the following, is how can we reproduce their results, okay? This is the first challenge. If you publish a paper and another person goes in the lab and tries to reproduce a result, if they cannot reproduce your result, they send you to court, they say that your results are not reproducible, you lied. Ti na ke rrejtneve, ti na ke gënyu. Pra shumë rëndësishme, ose është, për shembull, që të marrësh reproducible results, është goxha e rëndësishme dhe ç'a ndodh? Te pjesa eksperimentale, gjëja më e rëndësishme është kjo. Unë personalisht, unë do merresha gjithë këto informacione këtu, edhe do i hidhja kështu, sepse nuk mund të riprodhosh rezultatet e tjerit pa parë se çka ka përdor. Pra ka përdor Thor Labs laser helium neon. Kjo është helium neon laser. It's a laser which is commercial one. We transmit. Apparently, they've used a microscope objective. Okay, we care about this one. So, if you take this course with me, you should always include. Well, you are taking it already. You should always include this in the experimental parts what they have used. Okay. So apparently, they use a microscope objective, which is from company Newport. This is a part number. This is a numerical aperture. So they've used this one, and they use a pinhole, which is 5 micrometer. Okay. So why do we need a pinhole 5 micrometer? Apparently, they use this one. B is a diameter equal to this to remove spatial noise. Okay. Here they mention this one. But for now, we don't have a part number here, but we can search companies that sell pinhole apertures as small as a 5 micrometer, which is relatively small. And so let me see. So they have this, and they use a lens with this focal length distance. Okay, these are all essential or very important elements. The light is reflected by a mirror. So they use a mirror, they use a linear polarizer, followed by a beam splitter. These are a spatial light modulator. Okay, this is a company, very good company, Hollow Eye, and you have this here. Okay, SLM pixel size. What is SLM? Spatial space light modulator. Okay, so this modulates light in space, which means that if the light is propagating in this direction, you can modulate it in X and Y. Okay, so you are moving this way, but you are modulating it in a specific way. So this is SLM. Okay, so apparently they bought this SLM, Hollow Eye. Let's see what this looks like. And Andy, you have to do this one in detail, okay? So let's see what this looks like, this product. Great science. Let's check for the images. This apparently this could be this part, including the electronics. So these units, they need very strong. So this is the control unit of these products. But let's check here, Hollow Eye. Hollow Eye spatial light modulators. This is what we are talking about. Maybe the second link would be better. Let's check the second one, because this is the part number we are searching for. The 720, I don't know what does the 720 mean. Maybe it's the wavelength, lensless stock holography of the okay, category. That's what spatial light modulators. So this is the company that sells this product, but I wanted to see the way that it works. You can go to the publication, And then this is sync and sync. Sync, sync and sync. Okay, more information. So let's see here. On this product, more details are provided elsewhere. And you put here, you say sync and sync. What is the year? Sync and sync. We're talking about this paper. To me, it looks like this is 2000 and I cannot see it. 2018. Okay. So more details can be provided elsewhere in this paper about this product. Okay, let's go backwards, or let's go here where we were discussing our paper. So the experimental setup is very important. So they say also this SLM pixel size is 20 by 20 micrometer square. So it's 20 micrometer by 20. Okay. And the number of pixels is 1280 by 768. Okay. So they have a large pixel size. You can calculate how big this is. Okay. So this is like 1000. So what is this? How big is this unit? Let's calculate. This is 1000 by 20 micrometer. This goes something to 2400 një sekond shumë 2400 mikrometër, pastaj bëhet 24000 mikrometër, 24 milimetra, që është 2.4 cm. Pra pasi një komponent që është 2.4 cm me 1 cm, kaq i madh që e ke ky phase modulator, ose këto spatial light modulator. Spatial light modulators ndonjëherë kanë madhsinë tradicionalisht janë kështu. Shumica këtyre janë formë sferike. Pra mund të jenë sa 500 lekë ose 1000 lekë. Kjo si duket, kjo që nga formë drejtkëngsh, dhe drejtkëngsh që ka gati 20 mm me 10 mm, pasi në shumë zoom pikselet me 20 mikron që është pikseli këtu. Po me sa duket të përdorin vetëm qendrën e mesit. Pas e thotë SLM modulated light, okay, they use a buster camera which is with this part number. Now, what you have to do, Andy, okay, and all of you, is this. If there is an experimental section, even, I remember, you did the project core in the electromagnetic waves, you have done projects, I assigned these projects to you, and to most of you, I was trying to ask you to include also the price of the products. If you did a project in electromagnetic wave, if in this project there was something mentioning about fibers, optical fibers, I specifically asked you in the class, you didn't always do it, but I specifically asked you in the class to include the price. Go to the company who sells fiber optics, find the part number, send an email to the company, get the price. It could be, I don't know, 120 euros, but get that price. When you go to work a few years afterwards, this is what you're going to do. So in this case, we go to this Bastler A4A504K. Okay, here we have Bastler. I want to see how good is this camera. A504K. It's here. E shkruajtë në rregull, Bastler A504K. A504K. Let's see, Bastler Vision Technology. Ky është manuali na intereson neve. Si duket, përderisa s'doli Bastleri, ka mundësi Basteri se prodhon më këtë. Jo, do ta prodhoj se ky është paper e re. Bastler, no, what is this? Wood burning fireplace. Discontinued camera, yes. Duket që, sorry, this product apparently is obsolete. What happens is that often in electronics, if you have to design a circuit, you want to buy a chip, you want to buy an op-amp, you want to buy a RF enabled or Bluetooth enabled Arduino. Often these products are obsolete. The company that produced them initially, they are not producing anymore because probably they improved one component and they say that we're going to sell these new products. They don't sell it anymore. And what you can do for that is that you find it only from other company, from the websites of other companies. This is a little unfortunate. They should at least could have included, oh, apparently yes, discontinued cameras. Let's see if they provide information. We don't have time to go all over this, but this is 504 ishte kjo, 504 e ku që ka. 504 që ka këtu e gjetëm, që ka Ace series. Ace series, it's a high area of camera. I've seen these cameras before, but so Andy, you have to do this one, okay? So whatever part number is there, you should cut and crop this one, put it over there, and let's see Buster. But why should the respected research groups like these guys use a camera which is out of production? Maybe they bought too much of these, and they have still in stock. But I want to see now the pixel size. What is the pixel size? Pixel sensors. Okay, so okay, I think pixel size is 12 micrometer by 12 micrometer. This is huge, and this is the camera. Okay, so this is essential information that an engineer should read for. Actually, it's even written here. Okay, but I was expecting to get also some information about the price. The total used linear camera size of okay, so they provide, and this is then the optics. Now this is optics, and then all the rest is just computer science. Okay, so this is a paper which belongs to electronics engineering or someone who has some traditional knowledge on imaging. Not traditional. Yes, we can say traditional knowledge on imaging and how the experimental instrumentation works. But once you do deep learning, this part is computer science because this is the easy part, okay? And deep learning is really, now, it's, when I say it's easy, it's not that difficult, okay? Let me say it this way. Sometimes interpreting the results is also challenging. But now, okay, so here we see. So, Andy, in this case, you know what? You have to go and look at all of these products that we wrote here and pick up a price, okay? So check. If you have a pinhole aperture of 5 micrometers, what is the price? See what is this microscope objective? How much does this cost? Okay, try to get all of this information and write it in your paper, because apparently we noticed that some more information, especially where was this Sing and Sing? Sing and Sing. We said that more information about this product was provided elsewhere. Elsewhere. Where did we write it? Okay. So, Andy, you can also in this paper that you are going to submit the report, you can also add these. Now, this is how we start and write the how can I say, the report or the literature review. So, if you are going to write something about this paper in 2 sentences in your literature review, let me say also this: you don't write the master thesis with literature review by dedicating half a page to a single paper that you have read. Okay, you don't do it. That's too much. You can make it shorter. But in this case, if you are going to write something about this paper, you could include the following. Now, we wrote details here because we want to understand details over there, okay? But regarding this, you can say that these researchers from Sinha and the authors, they have acquired images of amplitude and the phase. They have used these images for training, and then during testing, they have provided only the amplitude information, and they have deduced what is the phase. And the phase is not 100% sure, okay? They are kind of predicting it, okay, from the features. So this is what we can say for this paper. We can add also this, saying that they have also conducted experimental work. So they have used spatial SLM. What was spatial linear? What was this SLM? Spatial light modulator. They have also conducted the experimental work. They found the results, and their results, we can extract them from the figures. Okay, so apparently they are putting also the, what is this, mean absolute error. So they report the error as a function of training time. Okay, so this is how you move around with the paper. Now let's start with Albert. Albert, can you go over your paper? And you read, we're going to follow you, okay? You had 2013 because we're doing this alphabetically. So this is the paper of Gastre.
Professor, I wrote it something. Can I send to you and you present, or just to then do it by scratch?
That's great. But Albert, why don't you read it? Whatever you have written.
Okay.
Mm-hmm.
Here in the abstract, Professor.
Okay.
I pointed out that Glasser and other authors on their paper about planoptic microscope based on laser optic feedback 2013 stated that LOFI, this is the microscopy presented in this paper, is presented previously on microlens array. Main properties of this technique, such as numerical refocusing on curved surface or aberrations, are both theoretically experimentally demonstrated with LOFI-based device.
Okay.
This is only about abstract. In introduction, I mentioned that authors of this paper propose that in planoptic imaging we can record both spatial and angular information, different from other conventional imaging setup, where only the position of incoming photons is recorded, while the information on the angle of arrival is lost. This results on extended field of view. We have some objective, the same objective aperture as other microscopes. It's not reduced. And also this gives us the opportunity of a correction of aberrations using digital post-processing. In this setup, the latitude of refocusing no longer depends on the resolution. Another advantage mentioned by authors is ultimate sensitivity, being shot noise limited.
Okay.
And thus is suitable for optically resolved imaging through scattering media where a few ballistic protons are available. All of this comes at the price of a slow acquisition caused by point-by-point scanning.
Okay.
This was about introduction.
Okay, that's good.
I have the conclusion also. I wrote it.
What did you write for conclusion?
Conclusion. In this paper, authors have presented a new technique of imaging, such as planoptic imaging used in microscopy. This technique proposed planoptic microscope as an efficient method of microscopy based on microlens array. Advantages of this technique are extended depth of focus and absence of trade-off, spatial or angular resolution. Talking about disadvantages of this technique, authors mentions that we have a slow point-by-point galvanometric scanning and degradation of photometric performances when target is not in the objective imaging focal plane.
Okay, is this all?
Yes, this is all.
Okay, that's good. Now, this is very interesting, these planoptic cameras. And we wanted to buy a planoptic camera here in our lab, Albert. And can you guess what the price could be for a planoptic camera?
10,000.
You are very close, actually. So you are correct. It was 20,000, but it's impressive how these cameras work because they record. Actually, you mentioned it. So they record the intensity, but they record also the direction. And what can happen with a planoptic camera is that you take the photo, and you have people at different distances, and one person at the front is in focus, and then after you have taken the photo, 1 month later, okay, you go to the photo, you click at the person who is at the back of the room, who is out of focus, and the camera can refocus 1 month later, because it has all the information where the photon is coming from. So this is very impressive way of imaging. These panoptic cameras, it's impressive actually, but that makes them 20,000 euros. Okay, they are very expensive. But I want to see actually what. Oh, so they are using panoptic microscope. Oh, okay, that's impressive. Now I wonder if we can use the panoptic microscope ourselves, because these panoptic cameras, they are huge. Okay, it's not that like you have a CMOS. You don't have just the detector, and you have a light gathering system. These are a little more complex. But can you check, Albert, whether these are commercial, these panoptic microscopes? Okay, so can you check also this one? The same way, like in the previous paper that we were going over the paper of Andy, I said that I'm really interested also in the price, who is selling, part numbers, and everything.
Okay,
So,
perfect. I will check.
Okay, thanks, Albert. Yeah, it was good. Now I'm really going over this paper because I was, yeah, actually in the title, is it? Let's see what they're talking about. Here they give the equations of the Fourier space, the signal in Fourier space by the phase filter. Okay, so they have a phase filter, which is this one, apparently. So, lock-in amplifier, common reference, okay, that's theoretical background. I think they don't give the product numbers, right? So they present a new kind of panoptic microscope. This is impressive. Really. Lofi microscope, reference 4. So Albert, could you have also a look at the reference 4 here? Oh, this optics journals, they have the reference at the top. So it's their own paper, so the same people. Actually, they look like French. Let me check their affiliation. Of course, they are Grenoble. So they report here synthetic aperture laser optical feedback image. Okay, this is a paper from 2012. Okay, thanks, Albert, for going over this one. But Albert, I strongly hope that you also have installed this Mendeley tool. You can use
Yes,
also.
I have, Professor.
You have
I
it?
did last time, yes.
So please use that one to insert the references. So you can immediately even pick up this reference 4, because you are going to tell the story, but you can also include this one in your references, the fourth one here, and more like this. So let me think for a moment. Okay, so right now we are just trying to understand how we read the paper, how we approach the understanding by looking both at the mathematical apparatus and also conceptually. So one story or one publication, you may understand it conceptually, okay? And sometimes it might happen that mathematical apparatus is very tough, it's very difficult. People spend years to understand it. People do PhDs on that. So sometimes we may not understand all of it, but we try to do our best, okay? So, but often there are really some specific problems that might be difficult, especially computational imaging is a challenging area, but it's not something, you have all the information, all the basic information that you took here in your bachelor study program, here with us. You have all the basic information. Don't be afraid of it. So in this course, I would strongly suggest, and probably we might go this way. So all of you might do some computational imaging implementation. How? With this, I mean you are going to run a code and you are going to analyze an input data or analyze some images or something. So get ready for it, and I'm going to assign to all of you specific problems, okay? We're going to learn how to do it, because let me say also this one. This research methods class is not only about literature review, okay, understanding, figuring out, you know, it's also about, you are students of electronics engineering. And I would like it very much so that you also build up on the general knowledge you have from your bachelor study program. Okay, this is what I hope to be able to do it all together, and I'll try my best to help you. Okay, in these, we have some experience with these imaging. Okay, we have the background information. We also have parts or components in the lab that you can always also implement with these. Okay, with these parts. We have a project, a very one relatively good project that we're working on, and if it is anything which is really beautiful, I don't know if you have time to buy new parts. We can buy them if you decide on something that you want to test. We can buy it, we can test it, we can experiment, we can have your own data set. Probably one semester is relatively short, but at least implementing, manipulating, or editing the codes for computational imaging, I would most probably you'll be able to do it by the end of the semester with the help of all the others in this class. Okay, we're going to learn from each other. So someone is going to report something, another student in the class is going to report something else. But at the same time, so both implementing in this specific area of which you already have the background, but at the same time trying to pick up general knowledge from the papers or from the different publications. Okay, I can thank you, Albert. We can go to Andy. Actually, the paper of Andy we already did it. So alphabetically, we go to Harid. Harid, can you go over your paper, or what did you pick up? Harid, can you go next? Okay. Sorry, I did not see. The mic is not working. Okay, don't worry, Harid. You can send it by email. Then, lucky Stefanos. Stefanos, go ahead. The floor is yours.
Well, I haven't written anything, Professor, because I wasn't catching what we were supposed to do.
Good. But why don't you have a look at the paper and let's read the abstract together?
I have the cluster phenoptic.
Okay. And by the way, you are shikon ekranin?
Yeah, po.
A duket, se unë pse më shoh veten aty, apo okay, pra I'm sharing the screen, u kujtova se atë po bëja. Në rregull. Okay, atëherë vazhdo, Stefanos, na thuaj cilin paper kishe ti? Ti kishe glastre, okay. Po ti kishe paperin e Albertit. Apo se kam gabim? Po e njëjta gjë, po sa zhuqelloj, se ti kishe marrë javën që kaloi, Alberti e kapi sot. Atëherë erdhi rradha Alertit. Alerti, what is your paper about? If it is. Wow, Alert, you have a wonderful paper. S'punon mikrofoni. Po mirë, Alert, dakord. Pa ke shkruaj diçka? Okay, so let's have a look at Alert's paper. So this is Nature Photonics paper. This is year 2019, so last year. Then let's see when this was submitted. Maybe we don't have time to see this. These are Institute of Bioengineering in France. No, Switzerland, sorry, EPLF. Of course, they speak French in Switzerland. Institute of Electrical Engineering. This is electrical engineering. You have Nonlinear Physics Center, apparently in Australia. Okay, so how many authors we have? We have quite a few authors. 1, 2, 3, 4, 5, 6, 7, 8. 8 authors. And they have worked on ultra-sensitive hyperspectral imaging and biodetection enabled by dielectric metasurfaces. Okay. So they are the dielectric metasurface. Meta surface is based on resonance sub-wavelength photonic structure, enabled novel ways of wavefront control and light focus and everything. Okay, recently emerged all that as Here it goes. Alerte, this is a sentence which is very generic, okay? But it says bound states in continuum were discovered in quantum mechanics, but were later employed as an important physical concept in static interference. Okay, okay. You know, photonic device, analyte sensor. That's good. Hyperspectral imaging, based biomolecule detection. Biomolecule detection. Okay, they use this technique, but alert. Can you also include what is their resolution? Actually, we can see the resolution right here. I think it is obvious here. So the spatial resolution, it's here, which is delta lambda resolution. This is what they mean here. And apparently, if this graph is to scale, kjo është nga 740 deri në 790. Ky grafiku, jo. Nuk e di apo e lexoj dot saktë, por ka mundësi, se tani po shoh për herë të parë, ka mundësi që ky grafiku këtu që e kam mouse-in këtu, mund të jetë to scale. Dhe nëse kjo është 740, po të marrë cop letër këtu. Po marrë cop letër dhe po e vendos mi monitor. Dhe mbi monitor mund del kjo letra është kaq. Nëse kjo është kaq, atëherë mund ngelet televizori do ishte goxha më mirë. Atëherë këto po palos ndysh. Kush na gjen atë delta lambën që është aty, sa është ajo vetë? Palosin dhe ndysh. Edhe një dysh. Ok, kjo I bie tjetë afërsisht, pak më e vogël se kjo. Po e quajmë 1/2. Atëherë këtë sa e kam testuar. Testim për 2. Kjo e gjitha është 50 njësi, pra kjo është 50. Testim për 2 25, testim për 2 12, pra kjo është 25, kjo është 12, kjo këtu është 6. Kjo është 6, atëherë okay, 6 nanometër. Pra rezolucioni që shohim këtu te kjo figurë që ka 6 nanometër. Por 6 nanometër s'është shumë mirë, jo prit, një sekond, çfarë flasim? 6 nanometër super mirë. Oh, they have a resolution of 6 nanometër. Në mikroskopi, objektet edhe nga fjala mikroskopi ose mikrobuz, mikrobuzi nuk është diçka që duket me mikroskop, është goxha I madh, por fakti mikrobuzi është gabim, por mikroskopia do thotë zbret në 10 fuqi minus 6. Por kjo nëse ne lexojmë mirë të grafikun, nëse kjo është 50 nanometër nga lart në fund, I bie kjo delta lambda që tregon këtu është 6 nanometër. Pra 6 mikrometër është një qelizë, 6 nanometër është 1000 herë më e vogël se një qelizë. Pra kjo shikon komponent shumë të detajuar të qelizave. Po si e bëjnë këto që çfarë është kjo resolution 6 nanometër? Si e bëjnë kështu? Kjo është that's interesting. Maybe we need to understand a little bit. There's the smallest pixel, which is here, and apparently hyperspectral sensing data cube. So they have a data cube, whichever way they define it, sensing resonance map. Here we see that resonance shift map here. This is delta lambda. It's 4 to okay. We need some work to understand this one. Narrowband tunable source. But what is a narrowband? What is the device that they use, or the light source? They use resonant. Okay. They have resonant sub-wavelength photonic structure. In fact, to understand these photonic structures, you have Professor Julian. Okay, so you knock in the door of Professor Julian, and he's going to teach you perfectly how this sub-wavelength photonic structure work. Okay. So broken in plane inversion symmetry. So if it is a sub-wavelength, resonance sub-wavelength, if the wavelength of light is, let's say, 300 nanometer or 400 nanometer, even if it is visible range, sub-wavelength is, of course, something smaller than this sub-wavelength. But now I'm trying to pick up whether I can see some wavelength in here. It's interesting. They have supercavity modes in near infrared here, wavelength. So infrared, red is 700. Infrared is beyond 700, maybe 1000. Near infrared is going to be somewhere in that range. Okay. Near-type resonances. Near-type resonances, this is an interesting element to read about. So there are some near-type, I think there are scattering. So when light does scattering from nanoparticles, it creates a diffraction pattern which can be analyzed. Okay. Anyway, so it looks like this is the paper that Alerti will work on. And but tonight, until 9 p.m., you have to send me by on Google Classroom. I'm going to open one section here so that you can send by email whatever you have done until now. Okay, half a page is perfect. It's fine. Just tomorrow until tomorrow afternoon. Where is this assignment? So tomorrow afternoon, you're going to send an improved version of what you assigned today. What is this? Paper review short version. Due date is today, time 9 p.m. I'm doing this one because later on I might forget. Okay. So let's do this assigned. But then you're going to have also an assignment which will be due tomorrow. Assignment. Paper review, long version. Okay. This will be due tomorrow, time optional. Okay, so this is all we can talk today. Actually, we can go over a lot of more material, and but I hope we can. So these are your assignment. I'm going to save this one, and actually, this document I have to share this with you on Google Classroom so they can go over our notes. Okay, all of these notes they were taken during the lecture, so you have heard this at least once, but we could have a chance to read them again, whatever we have written together. Then let's update our field. So if you work like this each week, by the end of the semester, you could have a master doc where you can include a lot of basic fundamental information, which will be useful for your thesis later on. Okay. Today, I was planning to talk also a little bit about the ethics of research, but probably if we start this one, this might take really a rock solid half an hour at least, but we can leave this one also probably for week 3. So in week 3, we could have something on ethics, or we can do it like this better. I propose to have them. So for next week, alert. Next week, we are going to make a presentation on ethics, okay? Alert, you cannot complain because your microphone is not working. Let's see if you have any comment. Weekly presentation on ethics. So we're going to start this one alphabetically. And ethics. And Albert, you get ready to talk about plagiarism in So where can the plagiarism be? Let me think. In the syllabus of our course, I don't remember it exactly. We can have plagiarism hypothesis, research question, okay. Results, okay. Results section, research question. I think we can call it like this. And Albert, can you identify if there could be some other type of plagiarism, okay? So sometimes, what I mean with this one, Albert, is the following. Sometimes just picking up, or so to say, stealing, this is not the best word, okay? For ose të përdorë si ti marrësh tjetrit research question, kjo është fakt goxha eveniment I madh. Pra, mundohet ta kapësh në këtë aspekt dhe shiko Albert nëse mund të ketë një element tjetër që mund të quhet plagiarism, që mund t'i kesh marrë dikujt tjetër ku diun. E të mëshme fare është result section. Ai ka një grafik që ka nxjerrë aty, ti t'ja marrësh pap ta kalosh te teza jote. Kjo është e lezetshme fare. Por mund të ketë elemente të tjerë të cilat mund të përbëjnë në esencë ndonjë lloj plagiarizmi. Okej, a ka ndonjë pyetje?
Profesor, tani te kjo do bëjmë një tip përmbledhje kësaj researchit ne.
Po. Aty pepi që keni marrë, po shiko, kur lexoni për atë, leximi do bëhet në kësaj natyre. Do lexoni dhe do mundoni të kuptoni diçka. Nëse s'kuptoni diçka, dhe për shembull ka dhënë referencë në një paper tjetër, shtojini edhe atë paperin. Për shembull, çfarë shkruajtëm te kur analizoj paperin e Andit, e thamë që okay, details about this they are found elsewhere. Mund të lexoni edhe atë paperin, që në rastin e Andit ishte sync and sync. Nëse ka pjesë eksperimentale, vendosni pjesët part numbers. Ndoshta s'keni kohë për të marrë çmimet, por ndoshta mund t'i shikoni diku. So we start with this. Ma dërgoni mua dhe unë do mundohem t'ju jap komentet, mirë. Po son deri në orën 9, me fjalë atë se ju ne në leksion jemi deri në orën 9. Por këtë pjesën e leksionit shfrytëzoni duke bërë këtë pjesën e analizës të paper review. Okay, konsiderojeni pra një punë cilën edhe ju do kontriboni gjatë leksionit. Ka ndonjë pyetje tjetër?
Do më thënë do bëjmë siç është ajo me introduction, me me gjithë strukturën që ka, po thjesht me fjalë më të shkurtra.
Po, mund ta thoshte, e vërtet, kështu do e bëni po. Do shpjegoni, do shpjegoni çfarë po ndodh. Pastaj ajo që është fantastike fare është kjo. Mundoheni të përfshini edhe ekuacionet. Në një tezë, se ju do shkruani tezën në vonë, ekuacione shumë esencial. Nuk do shkruani dokument Wikipedia. Edhe Wikipedia I ka ekuacione, edhe është shumë e mirë. Pra do të vendosni aparatin matematikor, do shtoni ekuacionet, do shtoni detaje, do shtoni për shembull prediction, ekuacione për shembull if this is the wavelength, if this is the size of the object, what should be the diffraction pattern, për shembull. Do të përdorni strukturë për review. Arriti për momentin, vetëm shkruani pjesë deskriptive. Fani. Okej, pra arriti për momentin të shkruani pjesë përshkruese. Do të thoni që në këtë paper autorët kanë shpjeguar këtë, përdoret këtu, ka këtë aftësi të mas, ka këtë aftësi të analizoj etj. Kështu pra. Ndonjë pyetje tjetër? Okej, nëse s'ka pyetje atëherë po e mbyllim me kaq për sonte. Por çfarë do thojë unë? But I'm here so that you can